Hi, and welcome to this quick review of the displacement and silver nitrate equations for Halogens chemistry for A-level. It's just going to focus on the equations rather than the overall periodic trends. That's covered in a separate video. The reason being is because this is the area where most people get a bit stuck, is remembering the equations and how to write them out. So I'm just going to focus on displacement reactions and the silver nitrate test. So starting with displacement reactions, that's to do with the relative reactivity of the halogens compared to each other. So that in itself depends on one thing only. So if you have a quick look at the relative sizes of the atoms, you're probably already aware of this anyway. If you've looked at any of my other videos on this subject, I'll have mentioned it already. So basically, the smaller the atomic radius, the larger the nuclear attraction because you have less shielding, and stronger the oxidizing ability. So let's now look at the displacement reactions themselves. So the basic idea behind displacement reactions with halogens and halides is that a more reactive halogen will displace a less reactive one from aqueous solution by oxidizing it. If you look at the diagram, you can see that there's an additional electron in the form of a cross that's been drawn on all of the halogens' original electrons. The chlorine atom's original electrons were drawn as circles or dots. So basically what we're saying is this. The chlorine atom had 7 electrons of its own to start with, and obviously what's happened is it's oxidized something else and gained an extra electron, which is drawn as a cross. Now because it's drawn as a cross, it shows it's different from the other electrons. It's important that if we were to do a dot and cross diagram that we do this. And the reason it's negatively charged is because the total number of electrons in the chloride ion, which is what we now call it, not a chlorine ion, a chloride ion, the total number of electrons exceeds the number of protons by 1. So let's now have a quick look at how the halogens compare to each other in terms of their ability to do this. So if we think back to the size of the atoms, we can now link that to oxidizing ability in terms of atomic radius and subsequent nuclear attraction. So what we need to be able to do is to predict what's going to react with what. So in order to predict what would react with what, you use the relative reactivity of the halogens like this. In other words, the further down the group you go, the less the number of halides below your particular halogen will be oxidized. So fluorine will oxidize everything else. Chlorine will oxidize bromide, iodide and astatide. Bromine will oxidize iodide and astatide. Iodine will only oxidize astatide, and astatine will not oxidize any other halides. It's also worth pointing out at this stage that when we talk about strongest oxidizing ability, that means that the converse is true. It would have the weakest reducing ability. So it's important, if you're ever asked about this, to be absolutely sure what the question is asking you about, and not confuse reducing with oxidizing. Okay, so now let's have a look at the actual equations themselves. This is the theory behind it. Now let's look at the redox equations and how you draw them out. And when we do this, I'm assuming that you'll be comfortable with knowing what's going to be reacting with what. So if we had a look at this little experiment, there's a clip for it, and it explains up in the top left-hand corner what's being added to what, and what reacts and what doesn't. The final results are in a photograph at the top of the page near the middle, and another version of doing this type of displacement can be seen in the photograph in the top right-hand corner, where we can do it in a test tube instead of a spotting tile, and shake it with some cyclohexane, and the displaced halogen gets drawn into the cyclohexane layer because it's non-polar like cyclohexane, and so it preferentially dissolves in the cyclohexane layer. So you can see the two solvents. So the halide ion is dissolved in the H2O layer, the halogen is dissolved in the hexane layer, or the cyclohexane layer. I should change that equation really, shouldn't I? Because cyclohexane is not C6H14. Right, that's better. Okay, so now we're going to have a look at the ionic versions of the equations in red. So the equations in red that are in the middle of the screen represent the equations for the reactions that have actually happened. So if we pop the animation on again, you can see that the reactions that have actually taken place are the ones here within the red border. Okay, so when you do an ionic equation, what you need to do is look very carefully at what appears twice on either side. So I'm going to do one to start off with, and then see if you can do the other two. So the way to do this is to draw out all of the ions involved, including all the species. So you've got chlorine aqueous on the left, bromine aqueous on the right, and the sodium bromide and sodium chloride can be split up into 2Na plus and 2Br minus, and then 2Cl minus plus 2Na plus, respectively. So if we now look at what can be cancelled both sides, you'll see quite clearly that sodium can be cancelled both sides. So therefore that leaves us with the simplest ionic equation of 2Br minus plus Cl2 giving you 2Cl minus plus Br2. So the explanation for this is that the chlorine has oxidized the bromide ions. So there are the simplest ionic equations with a quick explanation of what's going on in terms of oxidation. So finally what they might ask you to do is to do the redox half equations. So let's do those now. We're running out of room slightly at the bottom, so I'll try and stick to one or two. So the first thing you're doing when doing a redox half equation is working out what's been oxidized and what's been reduced. So like we've done before, we use oxidation numbers. You assign oxidation numbers to everything and decide what's been oxidized and what's been reduced. So just to recap, oxidation is when you get a drop in the oxidation number. Sorry, an increase in the oxidation number, beg your pardon. If you look at bromide going from -1 to 0, that's an increase. And a reduction is when you get a drop in the oxidation number. So for chlorine, it's going down to -1 from 0. So chlorine has been reduced to Cl minus, and bromide has been oxidized to bromine, just like what we've said under the simplest ionic equations section. So now what we can do is we can take that equation, that ionic equation, and split it into two half equations. So the half equations show what has gained electrons or what has lost electrons. So I'm sure you can try that out for the other two. We've done it for the first one. I'm sure the other two will be just as easy for you to have a look at. So you start off by drawing out the simplest ionic equation, put in the oxidation numbers, decide what's been oxidized and reduced, and then split it into the two processes. Oxidation, which would be the loss of electrons, reduction, which would be the gain of electrons. Okay, now the final part of this quick review is the silver nitrate reaction, and that's very, very straightforward. So we're just going to go and do that now. So the table shows the results of this test, what happens if you do the test. So what you have to do is add silver nitrate solution to your suspected halide, and the precipitate colour indicates the presence of either silver chloride, silver bromide, or silver iodide. As can now be seen labelling the photographs. So the white precipitate would be AgCl, a cream colour precipitate would be silver bromide, and a yellow colour precipitate would be silver iodide. However, problems arise when you start to think, what is the difference between cream and yellow? They can be perceived as quite similar by some people, and in addition, if you have a mixture of halide ions, could the colour of one precipitate be masking the colour of another? So as a further step to diagnostically confirm, what we do is we add ammonia. So if you add dilute ammonia, only silver chloride will dissolve. If you have concentrated ammonia, silver chloride and silver bromide will dissolve. So silver bromide can be eliminated by the addition of concentrated ammonia. And then finally, silver iodide will not dissolve in either concentrated or dilute ammonia. So if the precipitate doesn't dissolve in any concentration of ammonia, we know that silver iodide is present, and therefore the iodide ion must have been present to start with. So there's an ionic equation that goes with this as well. So it's worth pointing out at this stage that because there's no change in oxidation state, you can try it out and have a look for yourself. This is not called a redox reaction. Not all reactions are redox reactions. It's important to remember that as well. So now let's try a couple of practice examples just to sharpen your mind up a little and make sure that you're confident about this. So it might be worth grabbing a bit of file paper and trying these exercises just to see if you've taken on some of the basics of halogens and their reactions. The first one is about their properties, the second one is about specific displacement reactions. It's worth pausing the video at this point, and I'd say spend about 10 or 15 minutes doing this before you come back and try it. And I'll reveal the answers in a minute. So if you pause the video, give this a go, and then come back and see if we agree. Okay, so hopefully what you've been able to do is see that there's three of them where there'd be no visible change because there's no reaction. The reason for that would be because the halogen being added is not a strong enough oxidizing agent to oxidize the halide that's already there. For example, bromine will not oxidize chloride, iodine will not oxidize chloride, and iodine will not oxidize bromide. So as far as the others are concerned, chlorine with aqueous sodium bromide is obviously going to be this one here. Chlorine with aqueous sodium iodide is obviously going to be this one here. And bromine with aqueous sodium iodide, oh sorry, beg your pardon, let's take that back. Let's do that again. So chlorine with aqueous sodium iodide is going to be this one here. There you go. And bromine with aqueous sodium iodide is going to be that one there. Okay, so hopefully you found this clip, a shorter version of my bigger clip, reasonably useful. It just takes you through the equations and the reason why things react the way they do. For a bit more detail on the periodic trends, you can see my video clip called Periodic Trends Group 7. But this one was just mainly to take you through some of the basics, and particularly the equations, which sometimes people get a bit stuck with. Okay, thanks for your time again, thanks for listening, and see you soon. Bye.